Welcome back, everybody. We've been working through some material asynchronously, introducing some new concepts such as dictionaries and command line arguments, and working with CSV files using some of the built-in libraries. Well, today we're going to check in a synchronous fashion. So if you're not already on your house Zoom, I would encourage you to join up. We'll be working through a few exercises as practice and reinforcement when we reach them a little bit later in today's lecture. And we're going to use today to check in on where we're at in the course and go over how the previous quiz went. First, a few announcements. One, voting is coming up right around the corner, less than a month away. And in North Carolina, the registration deadline is tomorrow. So if you have not already registered to vote, be sure that you have a plan for doing so. And once you've registered, be sure that you have a plan for voting as well. The NC Board of Elections can be found through a quick Google search, and that will have more information on how to go about registration. If you're not in North Carolina, check out your local state board of registration and or board of elections, I should say, and be sure that you're registered so that you can cast your ballot. In the computer science department, we have a Hack the Culture Diversity Tech Networking Night coming up. And there are a number of companies that will be represented here: Google, CoStar, Epic Games, Red Ventures, Microsoft, Cisco, SAS. This is a who's who among folks who recruit locally at UNC for computer science majors and minors. And this is an event that's happening on Monday, October 12th. As soon as our lecture wraps up, I will post the slides with the links to all of this information, as well as the pre-registration link to the course website. We've got a few questions that I want to be sure that you're seeing them fresh for the first time when we reach them. So that's why today's lecture wasn't posted ahead of time. HackNC is a student-run hackathon where you are able to work with a group of peers on a project of your own design and creation. This is an officially sponsored hackathon where you're competing for prizes. And while you're in COMP110 right now, you might think, what might I get out of HackNC? And what can I do when there are senior computer science majors who are competing in this as well? Well, I would encourage you not to think about this as a competition so much as an opportunity to learn, practice, apply, and collaborate with peers. There are a number of talks that will be happening. There are workshops that will be led by some of the sponsoring companies and local tech leaders. And that's a good opportunity to learn. And I think just trying to work through a project with the skills that you have developed so far with a group of peers can be a great challenge and learning experience. The website is hacknc.com, and the application is pretty clearly linked to from there. All right, so I think that's all of the outside announcements. Next, I want to talk about how the quiz went and then introduce the next project, which is a weather statistics application that you'll be building to analyze some data. So let's talk about the quiz that just came up first. After that, we will be practicing diagramming and having some discussion around reference types, which are something that you actually have already been working with, but we need to talk about some more details of. So that'll be the conceptual content focus for today. And let's talk about how the quiz went. So the quiz was, by and large, a great success, and we appreciate all of the hard work you put into it. It seems like the extended deadline so that we weren't up against the time pressure was a good move. Some of you asked what was the mean, what was the median, what was the distribution like. So here is distribution of outcomes where each of the buckets in the top here is the first bar represents students who scored 90 to 100, the second 80 to 90, and so on. So more A's than B's. There were a good number of folks who cleared the passing line, but the last bit of credit for this quiz was based on getting some functionality to work. And I think there were just a few minor syntactical problems that led to some of these submissions not crossing that line. We are accepting regrade requests if you have a single line of code change in a submission that prevented your grader from passing those automated tests. Please do submit a regrade request on the function that this problem was encountered on in the auto grading part of the quiz, and we'll take a look at it. I'll talk about some resources for the folks who didn't reach the 60 passing bar, and things that you can be doing to hopefully cross that line on the next quiz in just a moment. So this is a fantastic outcome by and large. The mean was 80, the median 85. And one of the questions that's come up in COMP110 pretty frequently is, do you have to have prior programming experience to succeed in this course? Or how did the students with no prior programming experience before do on this particular quiz? So I would encourage you to think about this question for a second. Look at this data and what do you think, having seen this data, the outcome of students with no prior programming experience is? So the big reveal here is the data you're looking at is exclusively the results from students with no prior programming experience. If we included the students who did have prior programming experience in these outcomes, the mean went up by 4 points. So the 4 points higher for the mean, and the median about the same. So there's this notion that I want to say that if you have no prior programming experience and you are in the D and above range, you're doing great, right? And you're in fantastic shape, headed towards passing this course. For those of you who aren't quite crossing the line of the D or better on a quiz, like the most recent one, a reminder of some of the resources available to you. So we have 43 hours of walk-in appointments available with your TAs. At any given hour, we have at least 3, but sometimes up to 5 or 6 TAs working. We try and schedule that according to where deadlines are and things like that. While things are a little bit slower because we're just about to get into a new project, I would encourage you to come with conceptual questions. There's not as much of a time limit when there's no one waiting behind you for extra help. And we'd love to talk through what strategies you might apply for the next quiz to succeed on it. Tutoring is open tonight, and generally, as a reminder, tutoring is open in the evenings on Tuesdays and Thursdays after class ends, and then on Wednesdays in the afternoon. So I would encourage you to make use of these resources. The TAs and I are here to help you succeed. But by and large, those of you who have no prior experience, you are crushing it this semester in COMP110. This was the strongest quiz at this point in the semester we've ever actually seen. So let me talk about the next project, and then we'll get into the actual practice. So the next project involves weather statistics, and you will be implementing a program that parses some CSV data or processes some CSV data. That CSV data will be coming directly from an official agency, the National Oceanic and Atmospheric Administration, more commonly referred to as NOAA. If you are in environmental engineering or involved in the biologies, you've probably heard this term before. They're a large organization, and they have tons of data available to you. There's also just a really cool resource for other data and information about the ocean and the atmosphere. But specifically, there's a Center for Environmental Information that makes data highly accessible. And I'm not going to walk through all of the steps that you'll walk through in order to seek out your data set. But basically, you'll be finding data that is resourced from or sourced from an airport. And so each airport keeps a running tab. Every hour it records some data. And then there are daily summaries that are made up of like what was the temperature, the min, the max, how much precipitation was there, how much wind was there, things like that, right? And in your program, you will then you'll download a CSV that is a little bit more complex than the CSVs we've been practicing with, but this is what a real world CSV might look like. So there's a bunch of rows, if you look at a bunch of columns, if you look at that very top line. And then there's, a lot of entries in this table that might be blank. And if we actually use we look at this in a tabular format and visualize it, we'll see that some columns, if I go up or over to the left here, we'll see that each row corresponds to a recording. And most of these that have like FM 15 or 12 are hourly recordings. But the rows that have this SOD in it, and these are the ones we'll be focused on, and the problems or the project talks more about this. The SOD lines are summary of day rows, and those have daily statistics such as, the daily maximum and minimum dry bulb temperature. So that's what we think of as just the outdoor temperature, the wind direction in degrees, the peak wind speed, snowfall, all sorts of different statistics that we can analyze. And ultimately, your program will be one that you run at the command line. And let me just try and make myself a little bit smaller here so you can see. And you'll use command line arguments like we looked at in the previous lesson, where you say, okay, my program is PJ01 weather. The data file that I'm going to process is this CSV file that I've saved. And then two other arguments are, what is the column that you want to analyze and what do you want to do with it? So maybe we want to list the dry bulb temperatures that was the average for the day. This would be the average temperature that day. And you can also do things like find the average of that, and it will compute the mean for that given column of daily records. Right, so without going into any more detail than that, the point of this project is really just to get some comfort working with CSV data in a real world style program. This will be due Sunday the 18th, but to encourage and reward folks who get an early start, because getting an early start on this particular project is going to be important. We're offering a 5% extra credit opportunity if you get it in by Friday, October 6th. Right? This will post as soon as lecture ends, so look out for that, and I'll shoot an email through Sakai as well. All right. So with that, we're going to get into some practice with some of the concepts we've been looking at and introduce and focus a little bit more on this idea of what a reference type is and what it means. So I want to start out with a speed round here and challenge you all. I'm gonna have a countdown of 1:30. So go ahead and open up Poll Everywhere, and in Poll Everywhere, and the link is up top. I'm going to open up a 2 questions responses, right? And what I'd like you to try doing is reading through this code listing and responding to the 2 questions that are asking you about what the values, 2 of the values printed are, right? So I'm going to start the clock and go ahead. All right, it looks like there are still a few of you who are wrapping up, so I'm going to give another 30 seconds here and final answers for the 2 questions on Poll Everywhere. All right, great work on this. Let me show you the results from the very first question. The very first question is, what was the printed value of X? And 90% of you said 110. So let's try diagramming this and working through it. So I'm going to imagine that we are in a global frame, right? So we're going to be looking at call frames again in this particular video or in this particular lesson. Oops. And my pen is having a difficult moment here. 1 second while I restart my pen program. All right, there we go. So when this program is evaluated, what you'll see, what we know is that there's a globals frame that is set up. And because none of what we're doing in this first this first segment of code is inside of a function, all of the variables we're working with are going to be in this globals frame, right? And so in globals, we would see this X variable that's declared to be 110. And it's a float. And then we have Y, and Y is initialized to be whatever X is, right? So we need to evaluate this line. And whenever you see an assignment statement like this, we need to figure out, well, what is the value on the right-hand side of it? And here we look up, okay, we're in the global frame, it's 110. So we're saying assign 110.0 to Y, right? 110.0 to Y, okay? And then we are saying Y is right after that changed or reassigned to be 211.0, right? So this value is being assigned to the Y variable, and Y's value in this frame would update to be 211.0. When we reach this print X line, we would see that X is 110. And when we print Y, Y is 211.0, right? And I wrote over my decimal there, right? So you all said, 91% of you said 110 is what would be printed for X, and you are correct. Let's continue on from here. Now from here, there is a little bit less agreement on what the printed value of A would be. 77% of you said it would be 110 as a single element in a list. So notice we're using the list's literal syntax here, and this is saying this is a list with one element in it whose value is 110. And 23% of you said it'll be a list with one element in it with a value of 211. The reason why we're going to spend today focused on the idea of reference types is that only 23% of you actually got this right. And that's a surprising result. That's a sort of mind-blowing, the way that we're supposed to understand how this program and what you've told us about variables works seems to be breaking down here. And that is indeed kind of the case. When we work with reference types, which lists and dictionaries and objects are reference types, if they're mutable, like a list is mutable, we have to be very careful with how we reason through them. And we haven't addressed this yet. So there was no expectation that this would be correct, but I find it highly impactful to try and point out this sort of breaks your current mental model of how this should work. So let's identify, well, how does this actually work and why were we thinking that it would work in a different way? And then we're going to get another practice problem where you'll get to try applying this exact same concept on the very next slide. All right, so when we reach this line here, we're declaring a variable named A, and we're initializing it to a list of type float. And that list of type float has a single element at index 0 that is 110.0. Let me make this a little bit bigger. All right. And this is going to be in our heap, right? So just to label the spaces of the areas of memory, and this is our call stack, right? All right, let me make this globals frame big. I have a habit of making my frames too small. And what A is going to be assigned is a reference to, or a pointer to, this list value. And that list value is a list on the heap with a single element in it. So it would have a length of 1. All right. Now here's where things get interesting. And this is where the difference between reference types and value types really starts to take effect. When we set up a variable named B in our globals frame on the stack, what we're saying is assign to B whatever A is. Well, what is A? Well, the thing that I try to encourage as a best practice when thinking through diagramming and tracing a problem like this is to take very literally what is in the box on the stack for some variable, or what is the value referring to? And in this case, it's actually this arrow that is what A is. And so B is actually going to wind up being a reference to that exact same list. Now I'm drawing these two arrows to two different locations on that box, but I want to emphasize that they are both referring to that list in general. So with a reference type that's mutable, such as a list or a dictionary, and we'll see some others in the future, when we assign, we say A is going to be assigned to B, what we're saying is what A actually is, A is not necessarily actually this list. A is a reference to that list. So when we say assign A to B, we're saying assign the reference that A is to that list. That same reference is going to be assigned to B's value. And so B is now also going to refer to that same list. Now I want to pause here and emphasize that what we are not saying is B is a reference to A. And this is an important distinction to make because there are certain scenarios where this might work out momentarily. And in fact, it would work out in this example. But this breaks down later on. If we were to later reassign A to something else, this wouldn't work out. So we need to be careful here. And when we are saying A is being assigned to B, we're saying whatever reference A has in it, B is also going to have that same reference assigned to it. And so now when we continue on, it probably falls out as somewhat obvious that when we assign B index 0 a value of 211, so we take 211 and store it in B index 0, we change this item, we're mutating this list. And now when we go and we print A, well, A and B both refer to the exact same list object on the heap. So A is going to print 211.0 and B is going to print 211.0, right? And so this was an intentionally not intuitive code listing to try and trace through because this result is pretty surprising. So what I want to do next, before we go to practicing in groups, is go ahead and activate Poll Everywhere for Q&A on this specific code listing that we see here. If there are questions that you have on this example, given what we've said, go ahead and post them, and I'll give those questions a second to come in. Just to give a little bit more detail while waiting on that front about this idea of references, I want to talk at a lower level of how our machine is working under the hood. It's a little bit beyond our scope in COMP110, but gives you a sense of what this actually is and how this actually works. So in memory, every location in your computer's memory has some address associated with it. It's just a number, right? And so this X address might be, 0, this might be 1, this might be 2, this might be 3, and then this list might have a memory address of 400 million or something, and that would actually be a pretty small number, right? And I'm just making these up. These would there is a much more intentional way that these addresses would be laid out, but that's in an upper division course. And so if this list is stored at 400 million, what these arrows actually are numbers, right? So they're actually the addresses. So A would be 400 million, which is the address of the list that it's referring to. And when we said A is assigned to B, B would also be that same number, right? And so when we think about these references, while we're drawing arrows, because that's much more intuitive to think about how we might visualize memory in this way, really, these are just numbers that are storing the addresses of what we're referring to. And that's why these get copied in the way that they do, right? So a question just came in. I'm going to go ahead and revert this back because we don't need to be thinking about these addresses. That was a little bit of trivia and a highlight of what you might expect to see in a course like COMP110 Systems Programming. And so I'm going to draw those arrows back to this reference. So the question that just came in is, does tuple work in the same way, or is a tuple different? And that's pretty hard to read. I'll try and change those colors in the next break. That's a great question. So tuples, just like ranges, are immutable, meaning you can't change them. Strings are immutable as well, right? So with immutability, if you can't, since you can't actually change any of its attributes, the whether or not it's a reference or a value, that distinction kind of becomes nullified. This only matters because we can have two variables that refer to the same thing, and you can change it from either one of them. All right. So there's a question, another question that just came in. Now that we're introducing this heap space, which we haven't really spent too much time talking about before, all we've seen in the heap space prior to this question, or prior to this listing, were when we define a function, that function's definition in a language like Python lives in the heap space. Well, as we start to use objects, and list is an example of an object that's a data structure that's a compound type, those get stored in the heap space. And the reason for this is because you can imagine, like in this next project that you're going to do, you're going to be working with data sets that have start out with small numbers of rows, but you could imagine, if you wanted to store the entire history of a weather station from 1940 to 2020, there would be a very large list that would be storing all of those values in it. And it would be very expensive if we had to copy that list each time we called a function. So instead of having to copy each time we call a function and want to pass some list to somewhere else, computer scientists thought, why don't we keep these objects somewhere else and just pass around references to these objects. And that's great, but it introduces this potential for accidentally modifying one without realizing it. All right. So the next question is, if B were equal to, or sorry, the text is over, this pull everywhere is formatting is very hard to read. If B would instead be equal to a different list of floats, not A, would there be a separate list? Yes, great question. So let me actually give an example of that. So let's imagine that instead of this, I'm going to say that B is assigned a list that just has the value 0 in it, 0.0, right? And let me use blue. I think that shows up a little bit better here. So if we had instead assigned the list literal that had a single float literal in it, 0.0, we would have on the heap another list that has floats in it, and its index 0 would be 0.0, right? And if we carried this forward and we said, okay, B is now going to be this list. So we can have multiple lists on the heap. Each time you encounter a list literal like this, we're constructing a new list on the heap, and you would need to set up a new table for it to keep track of it in a diagram like this. So when we said B index 0 is 211, we would have updated only this particular list on the heap. And this would have still been 110. I forgot to reset that, sorry. So this list would have been 110 to begin with, which was A's list. And then if we had instead set up a brand new list for B like this, it's totally fine. We would have had two separate lists. The key distinction that we were looking at is when you say, hey, you've got a type of a variable that's a reference type, and list is an example of this. Dictionaries are also reference types that are mutable. When you say A, or you reference a variable name that has that reference, right? So we're saying this particular reference from A to this list object, B is also going to be that same reference. Now let me give you one other example really quickly. Imagine that we had one additional line here between after this B declaration and before the B is assigned, B index 0 is assigned to 211, and we had A is assigned another list such as 40, right? If we had this line right here, After B was set up, what would have happened is another list would have been entered into our heap and would have been created there. And I'm just going to write F for short for float, and we would have had at index 0, 40.0, right? And A would have been updated to refer to this brand new list, right? We would have been saying, hey, A is now assigned a new list. B would have still been referring to that initial list with A. And when we went to change B, we would have been changing, that initial list that had been set up, right? The next example that we're going to look at is going to have some additional practice here. Another question that's the top question right now, if you appended to B, would that also append to A? We're going to see an example of that very soon. The short answer is these are two aliases of the same thing. And so, you've got Kanye, you've got Yeezy, two names for the same person. Similarly, we can have two variable names or even more that refer to the same object on the heap. So anything that happens to one, the same thing they both refer to the same thing. So it's going to occur on both of them. So yes, if you append to one, it's going to append to the other. Is a value type a literal while a reference type contains a memory address? So when we think about literals, what a literal is what we're seeing here. This is actually two literals in one compound statement or in one compound expression, right? So the outer literal are these square brackets. And the square brackets are a list literal. And we're saying we're constructing a new list object. And so that's actually going to result in a reference to an object on the heap. The value that's stored inside of this, right, which would be, initially it was just 110 up here, this value, that's a value type. But this is a float literal. So the idea of a literal is really about you being able to write a piece of code or an expression in your code that literally evaluates to that particular value once the processor reaches it. So here what we're saying is this is a list literal that contains a float literal inside of it, right? And as we're working with compound types, we can do that. How would you go about assigning a copy of the list instead of the contents? That's a fantastic question. And there are some clever shortcut ways of doing this in Python that are idiomatic. But let me make a note to come back to this question later in lecture once we've seen a function that works with these, and this might be something to evaluate. I'll come back to that question. If we assign, okay, let me parse this question. So if we assign list index to a variable and then change the variable, would that change the list? Okay, great question. Love this question. This also gets right to the heart of it. So let me back up here and let's reset this so that it's where we ended before, right? So let's imagine now we had down here a variable like C is assigned A index 0, right? And I should have typed that as C is a float type, but I left that off for now. So C is assigned A index to 0. What happens here? Well, if after printing A and B, we reach this line and I needed to update to get us fully back to this point, I need to carry out this instruction. So this would have been 211. And now we're fully caught up with where we should have been. So we evaluate these two lines and those are printed out. And now we're saying C is assigned A index 0. Well, C is a float type, right? And let me actually write that out. Let me correct this. So C's type is float, right? And a float type is a value type whose value is going to live on the call stack. Well, when we try and evaluate what does this expression simplify to? Well, we look up A and then index. So A is we follow this arrow and then we look at index 0 means, okay, we're referring to the value 211.0. So it's as if we're saying, this is the same as saying C is a variable of float type that is being assigned 211.0, right? So this A index 0 would be substituted with 211.0 when the program is processing. and then 211.0 would be stored in this particular value. If you've got a float variable, it's always going to store a float value. You're never going to have a reference arrow in a float variable to refer to something else. So in this case, now we've got 2 copies of the value 211. If we changed list at index 0, it would be independent from the variable c. We've not set up any kind of relationship between them. The only place where relationships are established that in this way is when you have a reference type being assigned to some other reference variable. All right. Last question here, and then we're going to move on to a practice round in your zooms in breakouts. So if nothing else calls it out, would a list established in a for loop still have heap space? So this is an interesting question. So if you had a list that was being produced in a for loop and you never used it outside of that for loop or something else, would it still exist in the heap? And this is sort of like the question of if a tree falls in a forest and no one's there to hear it, did it really fall? And the answer is it's going to depend. In general, in a language like Python, it's still going to be evaluated because the language isn't clever enough to know what happens after the fact. And what happens, like that there might still be a chance that you would use it later in some way. In some other languages that get precompiled, there are some optimizations that might say, hey, it looks like you're never going to use this, and this was sort of a variable that never had any real purpose, and it would remove it from your program so that when you ran it later, it wouldn't be evaluated. But for our purposes, for thinking through how these things work, we are going to always, always, always apply the same step-by-step procedures and not try and cleverly optimize for anything that might be happening behind the scenes. Where the computer fundamentally is a very simple machine that's doing exactly what we tell it to. And so if we had some variable that we assigned some values and we never used it, the computer's happy to do that for us, and it doesn't know any better not to go ahead and follow the instructions we gave it. All right, great work and great questions on this. This is one of the trickier subjects in programming. And one of the driving reasons why we use these diagrams is because they really, really, really pay their dividends when we get to subjects like this, that if you don't have a diagram for this concept, which we didn't in the early days of 110, it's very confusing to work through. So what we're going to do next is I want you to try diagramming this particular question or this code listing with in a breakout group. So I'm going to turn it over to your house heads in your Zooms, and they might make a quick announcement about tutoring and encourage you to come. But then we're going to do breakouts, and I would encourage you to diagram this with your neighbors, and we'll work through it together just after that. 2 more minutes on this. It looks like about a quarter of you have checked in, having completed the diagram, but I want to give time for everyone to have the ability to try completing it. So check in on Poll Everywhere, and we'll get started again in 2 more minutes. All right, great work on this. Let's go ahead and talk through how this is going. It looks like over half of you were able to complete this, and hopefully, having just seen a similar exercise, we can translate that knowledge into how this works if we're working in another function frame. So here we actually need to remember to set up a frame for the main function when it gets called. I've gone ahead and set up in my globals frame a reference to the main function definition, which will be the function on lines 6 through 11, right? That's our definition here. And then what we assume when we're tracing these programs is that we're running them as a module. So we assume that this function call is going to be encountered because the special internal variable named name would be assigned the string main, both underscored. So we assume that this is going to be evaluated, and that means we need to set up a frame on our call stack. So we're going to have a frame for main, and the return address is going to be line 15, right? So we're going to come back to line 15, and there are no parameters to pass into main, so there's nothing else left for us to set up here. We're ready to go into this function. When we reach this function, we reach line 8, right? We skip over the doc string. That's just for documentation purposes. And here on line 8, we're saying, okay, we've got a list of integers that's going to be on our heap, and we're going to go ahead and construct that. It's got 2 elements in it, 0, 1, and the values are 10 and 20. And we set up a reference to that is assigned to the variable a, or the name a in the main frame is bound to this object or this list on the heap, right? So a is that reference, and that line is completed. Next, we see a line that looks just like what we saw before, where we're saying, okay, whatever A is, so we look and we see, okay, A is this arrow, right? And what I want to impress upon you is that when we're working with references, the arrow is what's important. That's what you should focus on. A is that arrow. It is that reference to this list. So when we say whatever A is going to be assigned to B, that means B is also going to refer to the same list, right? And these arrows, where they point to in this list, not important, right? We're referring to this list on the whole. So now the question that came up, which was a great foreshadowing from you all in Poll Everywhere, the question was, what happens if you append something? Well, here we're saying, okay, B is this reference to this list, and we're going to call the append method on it, right? So we're saying call the append method on this object B so that we append the value of 30 to it. We know that when we append a value to a list, it introduces a new index at the end of it. And because B and A referred to the exact same list on the heap, A was changed as well because they're just references to the same object, right? So that completes that. When we print A then, at this point, we would see the list literal representation that's 10, 20, 30 printed out. And then we reach the end of our main function. So there's nothing left here. We've reached the end of it. So our return value would be nothing. Our program would go back to line 15 where this function call occurred, and there's nothing after that. So this program has finished evaluating, and this is a complete evaluation. So I'm gonna go ahead and open up questions on this particular slide as well. And while I'm waiting for questions to come in, what I want to say is we're going to have one more of these where we're going to go to breakout rooms. And this next one's going to be important. This next one's going to be the one that I'd like you to submit on Gradescope. And the process for submitting one of these diagrams involves just scanning your paper or exporting a PDF if you're doing it on a tablet and uploading it to Gradescope. But we will have some of these diagrams on the next quiz. So the next quiz will be a combination of programming and diagramming to be sure that we understand how these programs are evaluating. So this is good practice to be in the habit of learning how to upload these diagrams to Gradescope because we'll be seeing that on the next quiz. Can I explain the return value again? Yes, great question. Okay, so it's been a while since we've talked about returning, and let's imagine if I back up here, we just finished printing out A, and that printed to our terminal 10, 20, 30. And now we've reached the end of main, right? Main is a procedure. Its return type is none. It doesn't have a return statement in it. It doesn't return any value. So when we reach the end of a procedure that has no return statement in it, we would say that the return value is effectively none, right? But none is kind of a pain to write out. So I often will shorthand it to just null or nothing. And effectively, it's not a value you would want to use. And so that's what the zero there is. Main didn't return any value. All right. Why would we ever want to use B? Great question. This is a fantastic question. And by the way, in the break, I was able to fix the formatting here. So why do we ever want to use B? And we look at this and we think, yeah, this is silly, right? So this is a short illustration of something that's a little bit contrived, right? This is a silly example. And the reason why this particular example was chosen in this instance is because it really boils down the mechanics of how this behavior works to this phenomenon of having references. And it sort of narrows in and hones in on the exact problem. In the next slide, we'll see something that actually is commonly done and is useful. One of the places where you might use references in a meaningful way. Where do we write terminal outputs in a diagram? All right, that's the next top question. That's a fantastic question. If we were asking you to diagram this as part of a quiz, we would ask for a column of output, or maybe down below your diagram, I would encourage somewhere just having an output column. And here it would have just been, 10, 20, 30. If this were a piece of paper or a tablet, I would have 3 columns. That gets a little bit tight when I'm trying to write on the slides when we're working this way. But I think having 3 columns, 1 column for output is handy. Why is return address 15 not like 8 and 9? Okay, so what is return address? Let's just review that very briefly. So this diagram is further along than this diagram is the program when it's completed, but it gives us a trail and keeps track of how we got to this point. And the way that it does that is, so notice we read in all of this, our definitions get entered, and then the processor reaches this line 14, tests whether or not this is true, and we're going to assume that this is true. So at this point, at line 15, this is where we reach the function called a main. This is what causes the processor to jump into the main function. And so when we set up a frame to handle a function call, we set up that return address to be the line that we're going to go back to when that function call is completed. So when the main function ends, because the return address was line 15, where that call occurred, that's where we'll go back to. You can think of it kind of like a bookmark. And this becomes much more valuable when we start having function calls that call other functions and call other functions, and we need to keep track of where we go back each time. Great question. How would you diagram a list of lists? I'm not going to, I don't want to get too hung up on that yet. That's a little bit beyond where we're at. We might get there next week. But the short story here is a list of lists would wind up having, it would be something like this, where you've got lists that have references out to other lists. So this would be a list of 3 lists where each of those lists had 3 items in it, right? So you would actually have arrows to other places in that way, but that's a little bit beyond where we are. So the next question is, if we reinitialized, if we had changed this, and this is a great question, and I'm actually going to need to, let's unwind this briefly, and then this will be the last question so that we have time to get through the next example. If we were to instead initialize B with 10 and 20 as well. So we set both of these up to initially have 10 and 20 in them, right? What this would have done is it would have constructed a separate list, right? And I'm not going to fully enumerate and draw that out, but there would have been a separate list. And when we called b.append, it would have appended to that list such that when we printed A, it would have been unchanged. So every time you see one of these, this list literal syntax, that means a new list is being constructed on the heap. And so these would be separate from one another, even though their contents were equal. If you have a global list and assigned a variable and changed it from within a function, would it append to the global? Yes. If you didn't, we'll talk more about this distinction between global and local scope in upcoming weeks. But if you're referring to the same list that was defined globally and you change it locally, it would have changed the global list as well. All right, these were fantastic questions, and I want to give you all an opportunity to try and diagram this final question of the day. And this is the one that you will hand in on Gradescope. So I would encourage you, it will be for effort. So we're still getting used to these. So don't stress out about it. But this one you should attempt, and we're going to do this in Zoom. So go ahead and start working with your neighbors. Those TAs will send you to breakout rooms. keep working. I'm going to go ahead and just get this diagram started, and then we'll come back at 5:52 to work through this together. One more minute, and then we'll talk through it together. All right, I know some of you haven't quite completed, and that's totally fine. This one involves parameter passing and a little bit more setup, but so that we can get through this in time for our lecture's end, let's go ahead and talk through this together, and then we'll take some questions. If we need to go a little bit over on questions, I apologize, but I'll be here for a few minutes after and can take those, and then this will be online and recorded. Additionally, I'll point out that because tutoring is tonight, if you have further questions and want to get into some of the details of this with a TA, I would highly encourage you to stop by. So I've gone ahead and taken this program to the point of line 11. We've set up our globals frame, we've set up main, the nums reference has this list that has the two elements in it, 0 and 1. I've set up my stack variables, start and stop, to have the values 2 and 3. And then we reach this function called to extend, which is where that particular program starts to get more interesting. So whenever we reach a function call, we know we need to set up a stack frame for it. So extend is the function that we're calling. And extend has 3 parameters as a part of it, right? It has x's, which is a list of integers. This is a reference type, right? So whenever we're assigning one reference type to another and we're initializing some reference type variable, it's also going to have a reference. And we're saying this expression here, nums, is going to evaluate to the reference to the list that has 0 and 1 in it. So this call to extend is also going to refer to that exact same list, right? So we're copying that reference to the x's parameter. And we have 2 more parameters to establish as well. We have a start parameter, and start is going to be assigned whatever start is in main. So we use name resolution, start in main is the value 2. So it's as if we're saying assign 2 to this second parameter, and then we would have a value of 2 established as the variable's value or the parameter's value for start in this frame. And so notice there's a difference here between our value types, which are copying the values, and our reference types that are copying the references. Same idea with stop, right? So stop will be the exact same story. Stop is going to get copied in. So stop had a value of 3 in the main frame, and we are copying that into the stop parameter of the extend function, right? So we've established our parameters. I didn't establish my return address. My return address is going to be line 11. So let me set that up. So RA is 11. That's where we're going to go back to when this function call is completed. But this frame is ready to go. So we now jump into the extend function and we reach a while loop. While start is less than stop. So we ask, is start less than stop? Is 2 less than 3? That's true. So we go into the while loop and we reach a method call. We're saying x's, which is this reference to this list, dot append. So we're going to append to this list. So we know we're going to have one more item added onto the end of it with an index of 2. And what are we appending? We're appending start. Well, start's value was 2, so we're adding an entry of 2 to this list, right? And then we reach a relative reassignment operator. We're saying take the current value of start, add 1 to it, and reassign that back to the start variable. Well, what start variable are we talking about? Here's where those name resolution rules apply. So we look in our current frame and see, is there a variable named start? And sure enough, there is. So we update this variable named start in the extend frame to be 3. So it's now 3. And we go back to the while loop and evaluate. Is start less than stop? Is 3 less than 3? No, that's now false, right? 3 is not less than 3. So we're done with this while loop. And it turns out we're done with this extend function as well. So the return value here is nothing because this is a function that returned none. It didn't have a return value, right? And so we return none and we go back to line 11, right? So the reason why we kept this address 11 is this is where we had left off. That's where we made that function call. And now we're ready to print nums. So we print, close out that box. We print nums, and this would be the list 0, 1, 2. Right? So a list of integers 0, 1, 2. And when we print start, now here's another interesting example of name resolution. When we're looking for the variable and how to resolve the word start at this point, what we have to do is we have to say which is the lowest frame on our call stack that has yet to return. So extend is done, right? It's completed its job. So we don't think of extend as an active function. So we look in the first function that's on our stack from the bottom up that hasn't returned is main. And this is the function we're evaluating currently, right? So we look in main for what is the current value of start. Well, start didn't change in main's frame, right? Start only changed. That was a variable in the extend frame. So the next thing that would print out is the value 2. Right? We then reach the end of main, and when that happens, we would enter the return value of none here, and we would go back to line 24, and then our program listing would be completed. I'm going to go ahead and open up questions, and as questions are coming in, just say a couple of things about this. So this example is really trying to illustrate some of the fundamental differences between passing in a reference to a parameter versus passing a value to a parameter. When you're passing a reference, that reference is getting copied. So notice that nums and x's in both of these frames referred to the exact same list on the heap. And so if we changed x's in extend, that meant we were changing nums in main, right? And so this is an example where we had a function that returned none, but it was still having some impact on that main function's outcome, right? Because we were changing the same reference. And this is contrasted with, in this example, the value types of start and stop and the parameters where we passed those values in by copying them. And when we changed one of those parameters in extend, we increased start by 1. It didn't have any impact on the start and main because local variables that and parameters are included in that distinction are separate from one another in the individual function call frames. All right. So I haven't seen any questions come in yet. While I'm going to give that one more minute, and I want to point out, oops, let me hide this for just a second, that in the Gradescope submission, there are some instructions for how to scan and create a PDF of a paper document from a free iOS app or a free Android app that's very handy to know how to do. This is something that when you often need to sign or send papers to someone else. Scanning them via one of those apps is really handy. All right. So the first question is, why did I not print nums? Let me highlight this line. And this line led to the output that you see right here. And if I were to draw, let me use a different color here because this is going to start looking like a crazy diagram. So that was the output of 0, 1, 2. And so nums is this particular list, right? And it just so happens we stored the numbers 0, 1, and 2 at the corresponding indices 0, 1, 2. That was a little bit of a coincidence here. But that's where I kept track of that. And so this was actually the printing of nums, and this was the printing of the start variable from the mainframe. And the second question is, why does start remain at 2? Or why does it remain at 2? So this will, it looks like those were the only two questions that come in. Let me address this one, and then I would encourage you, if you have other further questions, to stop by tutoring. So the key idea that we need to recognize about these frames is, let me change colors here and use maybe green. When we're working in the extend function, and the current active frame was this one, when we refer to this variable start, that name is bound to the variable start in that particular frame on the stack. And so we're referring to this start variable. That's why it changed. This line caused it to change to 3, right? Because this was the frame that was active. Well, when we're working inside of the main function, it has a separate variable named start that was what we were referring to when we used the name start here to call that function. And so as we write functions that have similar local variable names or similar parameter names, the key thing to be careful with is recognizing that between two frames or between two function calls, those values are independent of one another. So if you change one, it doesn't change the other. Even if they have the same name, they're unrelated to one another. The last question here was, did we say that changing x's and extend caused nums to change? Yes, those two values referred to the same list on the heap, and so changing one caused the other to appear as if it had changed. Working with references is one of the more tricky and nuanced aspects of working in a language like Python or Java, and these fundamental dynamics apply to these kinds of languages. Once you get comfortable with this idea that these mutable types like a list or a dictionary work with these dynamics, you can avoid some confusion by just being careful about where you pass these things and how you work with them. There's a question earlier on in lecture, how do you copy a list? And we didn't get to that question, and I apologize for that. But the gist is, one of the ways is you could write a function that returns a new list, and in that function you would set up an empty list, iterate through your input list, and copy each value one by one, and then return the new list from it. You can also use the list constructor, and maybe we'll have an example of that in the next lecture. Great work on today's questions, and there were fantastic questions that you asked today, and great work on these diagrams. If you have any problems or further questions, do stop by tutoring. Keep up the awesome work in the course. We were so proud of you all on the last quiz, and have a great, wonderful long weekend. Enjoy your mental health day. Take care.